Hi, in this video segment, I wanted to talk about a basic problem. This is mostly related to how we interpret the size of the key space. Sometimes I heard folks telling me that if we have a large key space, then the system must be secure because there are a lot of keys to brute force. It turned out that that argument is not really true. I'm going to take a simple historical example, the substitution cipher, and demonstrate to you that the substitution cipher has a large key space, but still it is possible to break it easily. So what is the substitution cipher? Substitution cipher is a very simple concept. Let's assume we are working with the English language, okay? And we only allow characters from our English alphabets A through Z, okay? It doesn't matter whether uppercase or lowercase, we don't distinguish. So it's just basically from small a to small z or capital A to capital Z, it doesn't matter. We treat them as the same. Okay. What is the idea of substitution cipher? Say you have a table, okay. You have two columns in this table. You have your A, B, C, and so on, all the way until Z, right? The idea of substitution cipher is that everywhere A occurs, you replace A by, say, U, B by V, C by X. I'm just selecting some random things, right? B, and so on. Okay. This is basically it. So suppose you're trying to encrypt message hello. How will you do that? You will go into this table, right? Say, let's assume Alice wants to send a message to Bob. Alice is here, and she wants to send a message to Bob. Okay, the message is hello. How can Alice do that? Alice and Bob must agree on this substitution cipher table upfront through some means. And then Alice will just to open her substitution table, look for a H. Suppose there is a H here and gets replaced to say C. Okay, so she will just replace H by C, E by whatever this table said. Let's say E was replaced by Y. Then she will replace E by Y. Let's say L is replaced by O. Okay, so O, another O. What about O here? And this O, let's say, was replaced by N. Okay, well, this must be here. by somewhere here, M. Okay, so she's going to send CYYOM to Bob. Now Bob has to take this and look at the substitution table he has. So one important property the substitution table must have is must be a one-to-one function. Otherwise, Bob wouldn't be able to recover the message Alice sent properly, right? Let's say I map A to U, B to also U. So you have a situation like this. A map to U, B map to U. Now from U, it's not clear whether A or B should be selected, right? This is not good. We are not allowing this. That's the reason why it has to be one-to-one. So this is basically the idea of substitution cipher. But let's reason about the key space of the substitution cipher. What is the key space? We can just view substitution cipher as a permutation, right? We are basically taking our A to Z and just rotate it, reorganize it a little bit. So it need not be a little bit, but it can be just a random rotation. Okay. So what you see here in this column is just nothing but A to Z reorganized. So it's one permutation, right? So how many permutations can you have if your alphabet size is 26? So let's take a simple example. What if the alphabet size is just 4? Okay. So you have A, B, C, D. There are, or even more smaller, 3 would be better. A, B, C. Okay. So if the alphabet is only A, B, C, what are the different permutations possible? Well, we can write all of them very quickly. It's only 6 possible permutations. Okay, we can leave A, B, C as it is. That's one permutation. We can switch B into C. That's another permutation. We are done with A. Similarly, we can just swap B and A, right? We can swap B with B as it is and C and A, right? And then we have the same C, A, B, and then C, B, A. That's basically it. So how many permutations did we get? We get six permutations. So we can actually reason about this in using a simple picture like this, right? So we have alphabet size of 26 for English alphabets, but let's take only 3. The first position can be filled in 3 ways. The second position can be filled in 2 ways, and then remaining only 1. So totally 6 different ways. 3 into 2 into 6 into 1. Okay, not 3 plus 2 plus 1. Okay, it's 3 times 2 times 1. So if you have 26, basically you have something like this. You have the first position can be filled in 26 ways. Second is 25. Third is 24, and so on, all the way until 1. Okay, which means there are 26 factorial possible ways this table could have been constructed. So an eavesdropper who's looking at this particular gibberish cybertext has to perform 26 factorial possible brute force to figure out the plain text. Okay, so it's a large key space. What is 26 factorial approximately? 26 factorial turned out to be approximately equal to 4 times 10 to the power of 26, which is, we can even more, let's assume 10 is approximately 8, just to make it 2 power, right? So it's 2 power, so it's 2 power 2 here, and here it is 2 power 3 means 2 power 78 already, which is a large number. We can see it's 2 power 80, right? Even for a computer, 2 power 80 is a large number. It's more than 2 power 80, but it's okay for our discussion here. So it's infeasible even for a modern computer to try 2 power 80 possibilities. In cryptography, we usually aim for 2 power 128 possible work, but for our discussion here, it's enough. So the main message is that if you have a cipher like a substitution cipher, you get a large key space. But let's think about the attack. Okay, you probably notice very simple information leakage here. You saw here it's OO, clearly mapping to the same pair of adjacent letters, right? If a letter is repeating in your plain text, it will repeat also in the ciphertext. So that's one information leakage. Right away you get that. And we can do more frequency analysis. For example, it turned out that in the English language, I believe the same true for other languages as well, E, T, A, for example, occur more frequently, okay, comparing to other letters. That means you can just do frequency count on the ciphertext, count how many times a particular every letter occurs, right? Count here, this occurs once, this occurs once, this occurs twice, this occurs once, and then try to map the most frequently occurring ones based on a frequency table that is sort of empirically validated on large volume of data. And you can also try the 2 grams or 3 grams, like, okay, for example, the letter T followed by H is more frequent because the is frequent. So you can do all those kinds of small frequency analysis tricks to recover the plain text. So despite the fact that you have a large key space of 2 power 80 possibilities. Okay, so large key space is necessary but not sufficient. That is basically the main message